So we've got our setup from last time, and I'm just going to look at the classical predictions, what a classical physicist would have predicted would happen with the photoelectric effect. Remember, this is before all the stuff that Planck came along with quantization of light. Everyone at this point still thinks that light is a wave. Before we do that, I'm just going to change one thing here. This value, 10 joules, that I just made up last time is ridiculously big for a work function. It's more like 10 to the minus 19 joules. So we're going to use the unit that we looked at last time, or in previous time to that, the electron volt. That's the whole point of having electron volts. So I will still make it up, 3 electron volts. But that is that's an amount of energy, K3, which is equal to 3 times 1.6 times 10 to the minus 19 joules. So what's that, 4.8 times 10 to the minus 19 joules. Okay, it's just a nicer number to have 3. But it's still an amount of energy, and I still can talk about this in the same way if I give this electron 3 electron volts of energy, which is 4.8 times 10 to the minus 19 joules. But it's nicer to say 3. If I give it 3 electron volts of energy, it can be liberated, ejected from the surface of the anode, and then it's a photoelectron because that's been caused by light, and now it will flow. It can flow through this circuit, make a photocurrent. And I do that, as I said before, I do that by shining light. Here's a blue light. I can shine that light on that. If it gives that 3 electron volts of energy, a current can flow. The other term that I'm going to introduce is this Kmax, which is the maximum kinetic energy of a photoelectron. So when we have that electron absorb the energy and be ejected, it's ejected with some speed, which can be calculated, and we can get a kinetic energy for that. So we have a kinetic energy Kmax for the electron. All right, let's look at the classical predictions. Okay, so everyone still thinks light's a wave. If light's a wave, how's it going to behave in this situation? What's going to happen for the photoelectric effect? Well, the first one, which was the first one that I got you to do in the notes, is to do with the brightness. If I shine a brighter light, so keeping the wavelength of light, the color of light the same, the brighter the light, the higher the maximum kinetic energy will be of a photoelectron. Brighter the light, higher Kmax. Okay, so the prediction is if I shine, let's say, one beam of this blue light here can represent just a very dim light, and I can get a photoelectron to be generated from that. I can measure the kinetic energy of that electron and find it to be some value. But then if I do this, shine a really bright blue light. Okay, so it's exactly the same color. I'm not changing the wavelength of the light. I'm just making it much, much brighter. Okay, so much, much more light coming down. All right, it makes sense. More light means more energy. More brightness means more energy. And if that energy is going into this electron, well, then it's going to absorb more energy. It's going to be going faster. So whereas with one, it might have been going like that, kinetic energy. With this much light coming in of the same wavelength, it should be going really fast because there's just more energy. Okay, that's the first prediction, classical prediction. The brighter the light, the higher Kmax, without changing the color of the light. The second prediction is that any color, I'll make that a bigger font, any color would produce a photocurrent. So any color, any wavelength of light can produce a photocurrent. So why does that prediction make sense? Well, what do I need to do to make a photocurrent? I need to give this electron 3 electron volts of energy. All right, so if I take my red light, my low energy light, remember red's low energy, which is low frequency or long wavelength, high wavelength, and shine it on. It might take a bit longer. Okay, I might have to shine that on for 5 minutes on there, but eventually I'm going to shine enough energy on there that I get up to 3 electron volts. Maybe it takes 20 minutes. It doesn't matter how long it takes, but eventually I should be able to get to 3 electron volts. And then once I have 3 electron volts, this photoelectron can be liberated and off it goes. All right, let's say it takes 20 minutes of shining red light onto that for that amount of energy to be delivered. Well, if I now take my green, what do you expect is going to happen? Well, it's going to be a shorter amount of time because this is higher energy light. So maybe it takes 10 minutes of shining this on, and then I get all the electrons. Then the 3 electron volts is delivered, and the electrons start to move. And if I take the very high energy light, maybe it only takes 30 seconds for this one to start to get a photocurrent flowing. But it doesn't matter what, and I could extend that both ways out of the visible light. I could go down here to the infrared, okay, or even the radio. I could put radio waves onto this for a few hours. Eventually, I would get up to 3 electron volts. And going this way into the ultraviolet and beyond, maybe it only takes like 5 seconds of shining ultraviolet light on there before electrons start to move. So it doesn't matter the color of light you use. Eventually, any color will produce a photoelectron. They're the 2 predictions that you get from the idea that light is a wave. And they're both wrong. Okay, so let's make sure we understand that. Wrong. So what actually happens? Well, let's look at this first one. You take the blue light and you shine a very dim blue light on there. You measure the maximum kinetic energy of this electron to be some value, and then you shine the same color light, but much more of it, so much brighter light. You get photoelectrons, you measure their maximum kinetic energy, and it's the same value. Okay, the maximum kinetic energy does not change with the brightness. The weakest light will still give the electrons the same energy as a really, really strong, bright light. Okay, and classically that doesn't make sense because a bright light has more energy than a weak light. Why doesn't the electron then have more energy? All right, that's the first thing that went wrong. And the second thing about the colors, let's talk about, rather than talk about the wavelength of these colors, I'm going to talk about the frequency. Okay, so red has a low low frequency, a high wavelength, low frequency. So this is, let's say, low F. Green has a middle wavelength, middle frequency, so mid F, and blue has a high frequency, short wavelength, so I'd say high F. So frequency is proportional to the energy. Remember from the formula, E equals HF. Okay, essentially when you talk about frequency, you're saying the energy. Low F, low frequency, low energy. High F, high frequency, high energy. And so I take my force, and this is for some particular anode. So the anode material makes a difference. We'll look at that in the next video. We'll look at that. But I take my low frequency red light and I shine it on there, and I can shine it on there for 1 minute, 5 minutes, 10 minutes, 2 hours, 5 years. Nothing will ever happen. Okay, it's too low energy. So even though you would think, the energy is going to build up, eventually I'll reach my 3 electron volts. that never happens, and you never get a photoelectron from using something that's too low. Then maybe I take my mid frequency, my middle energy light, and shine it on, and then immediately I get photoelectrons. Okay, it doesn't have to build up. Immediately, photoelectrons start to be ejected and flow and get a photocurrent, and they have some kinetic energy, Kmax, and then any frequency higher than that first frequency where that happens. So maybe if I even make this a bit more, let's do it like this. Let's put an orange in. And so red, orange, forget yellow, we've got green, and let's do it like a lighter blue as well. There we go. So in terms of energy, that's still kind of in the same order. So I take my red, shine it on there, nothing happens no matter how long I leave it. Take my orange, shine it on there, nothing happens no matter how long I leave it. Take my green, immediately I get photoelectrons. Okay, and then anything higher energy or higher frequency than the green, again, produces immediate photoelectrons. So immediate photoelectrons from light blue, immediate photoelectrons from the darker blue there. What's right at the end? Violet, immediate photoelectrons from violet. If I went even higher, ultraviolet, X-ray, etc., immediate photoelectrons. So there is what's called a cutoff frequency, or a threshold frequency, actually is the more common name. The threshold frequency. In this example, it will be whatever the frequency of this green light was, is the threshold frequency, where below that frequency you don't get any photoelectrons, and then above that frequency, so the orange and the red, they didn't give it photoelectrons, that reached the threshold frequency, now I get photoelectrons, and then every frequency higher than that I get photoelectrons. Is a cutoff frequency or a threshold frequency.